Quantum physics is a branch of physics that deals with the behavior of matter and energy at the atomic and subatomic level. It is a very strange and counterintuitive branch of physics, and it can be difficult to understand. However, it is also a very important branch of physics, and it has led to many important discoveries and technologies. Quantum physics was born in the early 20th century, when a number of scientists began to realize that classical physics could not explain the behavior of atoms and subatomic particles. One of the most important early discoveries in quantum physics was the discovery of the electron by J.J. Thomson in 1897. Thomson showed that electrons are much smaller than atoms and that they have a negative charge. Another important early discovery in quantum physics was the discovery of the quantum of energy by Max Planck in 1900. Planck showed that energy is not continuous, but is instead made up of small packets called quanta. In 1905, Albert Einstein published his famous paper on the photoelectric effect. In this paper, Einstein showed that light is made up of small packets of energy called photons. In 1913, Niels Bohr proposed a model of the atom that explained the emission and absorption of light by atoms. Bohr's model was a major step forward in our understanding of quantum physics. In the 1920s and 1930s, a number of other important discoveries were made in quantum physics. These discoveries included the development of quantum mechanics by Erwin Schrödinger and Werner Heisenberg, and the discovery of the uncertainty principle by Heisenberg. Quantum physics is based on a number of fundamental principles. These principles include wave-particle duality. This principle states that matter and energy can exhibit both wave-like and particle-like properties. For example, electrons can be diffracted, which is a wave-like property. However, electrons can also be detected as particles. The wave-particle duality of matter and energy is a very strange and counterintuitive concept. However, it has been verified by many experiments. The popular technology of X-ray diffraction is based on the wave-particle duality principle of quantum physics. In X-rays diffraction, X-rays are used to determine the structure of crystals and molecules. X-rays are diffracted by the atoms in a crystal, producing an interference pattern that can be analyzed to determine the arrangement of the atoms. This technology, which is based on the quantum principle of wave-particle duality, is used in materials science, chemistry, and biology to study the structure of proteins, minerals, and other materials. Next is the principle of quantization. This principle states that energy is not continuous, but is instead made up of small packets called quanta. The quantization of energy was first discovered by Max Planck in 1900. Planck was studying the emission of light from hot objects. He found that the energy of the emitted light was not continuous, but was instead made up of small packets of energy. The quantization of energy is a very important concept in quantum physics. It is responsible for many of the strange and counterintuitive properties of quantum systems. Quantization is closely linked to the wave-particle duality of matter and light. Particles like electrons can exhibit both wave-like and particle-like properties, and the quantization of energy is a manifestation of their wave-like nature. The principle of quantization is a cornerstone of quantum mechanics, providing a framework for understanding the behavior of atoms, molecules, and subatomic particles. Modern-day lasers operate on the principle of stimulated emission, where excited atoms emit photons of the same energy and phase. This process relies on the quantization of energy levels in atoms. Next up is the principle of superposition, which states that a quantum particle can exist in multiple states at the same time. For example, a quantum particle can be in a state of both spin up and spin down at the same time. This is a very strange concept, but it has been verified by many experiments. The superposition principle is responsible for many of the strange and counterintuitive properties of quantum systems. It is also the basis for quantum computing. Then comes the principle of entanglement. This principle states that two quantum particles can become linked in such a way that the state of one particle depends on the state of the other particle, no matter how far apart they are. For example, two entangled photons can be separated by a large distance. However, if the state of one photon is measured, the state of the other photon will be instantly known. Entanglement is a very strange and counterintuitive concept. However, it has been verified by many experiments. Entanglement is also the basis for quantum communication. This principle can be used for secure communication channels, known as quantum networks, that are resistant to hacking. The principle of entanglement can be used in quantum cryptography, where this principle can be used to create unbreakable encryption schemes, as any attempt to eavesdrop on the communication would disturb the entangled state. Then comes the uncertainty principle. One of the most important consequences of quantum mechanics is the uncertainty principle. This principle states that it is impossible to know both the momentum and position of a quantum particle with absolute certainty. The more precisely you know the momentum of a quantum particle, the less precisely you know its position, and vice versa. The uncertainty principle is a fundamental limitation imposed by the laws of quantum mechanics. It challenges our classical intuition about the nature of reality and has profound implications for our understanding of the universe. The uncertainty principle is relevant in quantum optics, where the properties of light are studied at the quantum level. Besides, this principle also plays a role in understanding the behavior of nanomaterials and devices, where quantum effects become significant. Quantum physics is still a very active area of research. There are many unanswered questions in this field. However, quantum physics has potential to revolutionize various fields, leading to groundbreaking technologies with immense potential. You must have heard of quantum computers. Quantum computers promise to solve complex problems exponentially faster than classical computers, with applications in fields such as drug discovery, materials science, and cryptography. While still in its early stages, quantum computing has shown significant progress, with companies like IBM, Google, and Intel developing powerful quantum processors. Then there is quantum cryptography, where entanglement can be used to create unbreakable encryption keys, ensuring secure communication. Quantum cryptography is ideal for protecting sensitive information, such as financial transactions, government, and military secrets. The principles of quantum physics can be used to build quantum sensors that offer unprecedented sensitivity and precision, with applications in fields like medicine, environmental monitoring, and navigation. Currently, quantum sensors are being developed for applications such as detecting gravitational waves, measuring magnetic fields, and imaging biological molecules. The principles of quantum physics can be used to develop quantum materials, quantum metrology, quantum simulations, and even quantum internet. The potential is immense. These are just a few examples of the exciting applications and technologies emerging from quantum physics. As research continues to advance, we can expect even more groundbreaking developments in the years to come. What are your thoughts about quantum physics and its future applications? Let me know in the comments below. Don't forget to like this video and subscribe to this channel.